Okay, so hello everybody, I'm Richard Southwell and today I want to start a new course. So the name of the course is Experimental Complex Networks. You probably won't find another course with that name on the internet because it's kind of a new idea. Basically, what I want to do is to do a kind of exploration of the different kinds of forms that can be generated, the different kinds of network forms that can be generated by very simple computational processes. Now, if you have a look at some of my other videos, you might see that I'm very interested in string rewrite systems, and I have considered a few different ways that complex networks can grow from simple rules. But in this course I'm going to go through a few more other different ways, more methodically. And so basically I've got a few different objectives. Firstly, I want to show you a lot of different ways to make interesting complex networks and shapes from very simple rules. And I want to do that in an easy way. I don't want to have to teach you abstract algebra and manifolds and all the rest of it. I just want to give you a very, very simple explanation of some kinds of network growth mechanisms. Secondly, I want to show you these network growth mechanisms working, and I want to show you all kinds of different forms that can be created. And I think you're going to be surprised by the diversity of different kinds of structures that can be created. And thirdly, I'm actually going to sort of create some real examples. For example, here are a few different networks which I've been generating using a few of these different things which I shall be discussing. And I'm actually going to be creating models and talking about the actual models. So this is really going to be a hands-on course. There's not going to be any requirements for knowing a lot of algebra or anything like that. So I think anybody should be able to follow this course. And this is basically what we're going to do. And then the last point, which I'm going to try and do as we go along, is to suggest applications for these different kinds of systems which I'm going to be talking about. So basically, in a nutshell, there is a massive space of network growth mechanisms, and what we're going to do is we're going to go into that space, we're going to have a look around, we're going to find some network growth mechanisms, we're going to watch them, and we're going to think about what we can do with them. And I'm hoping that you're going to find this pretty interesting. I think it's pretty interesting because the great thing about it is that very often you don't really know what's going to happen. When you get a new growth mechanism and you run it, sometimes it can make something totally boring, sometimes it can make something absolutely fascinating. So you might be thinking then, well, what's in it for me? What do I get out of it? Well, what I'm hoping that the viewer's going to get out of this course is a few things. Hopefully gaining some kind of understanding about what kinds of growth processes and what kinds of structures can come about from these kind of simple rules. And this knowledge is quite special because it's not widespread. I don't think very many people, if anybody, really understands in a very comprehensive way what kinds of forms come about via simple growth rules. Actually, I think that the entire question is sort of formally difficult to understand. Because if you think about things like biology, if you think about all these different organisms that grow, lots of those have simple mechanisms behind the growth of a thing. But that doesn't mean that it's easy to understand how all these different organisms grow. It's almost exactly the same with the world of network systems. So you're going to be getting some intuition about what kinds of ways that these different forms can grow, and you're going to be getting some links with some other kinds of systems which you might have thought of in a completely different context. For example, I'm going to be looking at some very simple systems to do with numbers, but we're going to look at them from a network context. So it's going to look different and it's going to make some new connections there. And also, for the artists among you, we're going to be having a look at how we can exploit some of these different kinds of forms and networks to actually make some useful or beautiful shapes. And that's actually the angle which I'm most interested in. I think that over the future, there's going to be more and more and more of this kind of looking what simple programs do and then using that to create art or to create useful objects. So here are just a few of the kinds of networks which we're going to be looking at, and we're going to be talking about these kind of things in detail. Now, as I say, I'm not going to be getting into the sort of rigorous theory. I'm not going to be talking about much to do with maths at all, really. I'm mostly just going to be talking about shapes and ways things grow and very intuitive ideas. So I hope you'll enjoy the course.
Okay, so I'd like to talk about these systems today, which are called multi-way systems with numbers. I'll talk about the history and terminology in a second, but let me just start by explaining what these systems are, because really the idea is extremely simple. You have two different operations, say a red operation and a blue operation. So this red operation here is 3x. This means times by 3. And so this gives you a load of edges. So there's a red edge pointing from 1 to 3, because 3 is equal to 3 times 1. Timesing by 3 again, we get 9. So there's a red edge pointing from 3 to 9. And there's a red edge pointing from 3 to 27, and so on and so forth. And so this kind of 3x function here, this kind of makes all these red edges happen. You see, there's the red edge pointing out to 40 points towards 120, because 120 is equal to 3 times 40. So basically, we've specified this kind of operation here, this 3x operation, and this has made a load of red edges happen in our network. Basically what it means is that every number has a red edge pointing from it to 2 to 3 times that number. Okay? So if that's all we did, we'd get a very boring network, but we also added in an extra thing. We added an extra kind of 2x function as well. So we have these blue edges representing multiplication by 2. So 5 points to 10, 10 points to 20, 20 points to 40, etc. These blue edges represent multiplying by 2. And so you can see that just by having these two operations, we already get a kind of interesting network structure. So here we have all of the numbers less than 128, I think, and we can see that we've really got a fairly interesting kind of space being created already. Now, you can think of this as a sort of directed space, if you like. You see these are directed arrows. The line from 1 to 2 is directed, and the line from 2 to 3 is 2 to 4 is directed, and so on. So that's one thing to notice. Of course, whenever you apply these operations, these numbers are getting bigger, so there's not going to be any way to go back to where you started from. Another thing to notice is that we have this kind of, we have a lot of things that look a little bit like squares. I mean, if you forgot about the fact that these are arrows, then you'd say that there's a lot of squares in these kind of networks. And there's a good reason for that. Basically, the reason is that, for example, if you want to make 36 out of 6, there's two different ways to do it. You can multiply it by 3 and then multiply it by 2, or you can multiply it by 2 and then multiply it by 3. And so that's the kind of reason that we have all these sort of diamond shapes appearing. Well, okay then, so this is a fairly interesting kind of multi-way system. Here, our red operation is 1 plus x. Okay, so the red arrow pointing out of a number points towards 1 plus that number. So there's an arrow from 10 pointing to 11, and from 11 pointing to 12, and so on and so forth. Whereas on the other hand, the blue arrow points towards twice the number. So this is one of my favourite multi-way systems with numbers, because the two different kinds of operations involved are very simple. But I think that the actual structure being created is pretty interesting. So the red arrows is just 1 plus x, and the blue arrows just represent 2x. And yet we get this fairly elaborate kind of spiral pattern. And it actually seems to, for the most part, look like it's doing some kind of tiling of the space into these, they're pentagons, aren't they? They're 1, 2, 3, 5. Yes. So we're really getting quite a lot for our money here. I mean, we've only put in a couple of very, very simple functions, and we're seeing spirals, and we're seeing some kind of tiling of the space. And I think it'd be very interesting to try and find a nice way to set out these numbers here. I mean, this actual diagram, as many of the diagrams I shall show you, have been created using a graph embedding algorithm. Basically, Mathematicas' spring embedding algorithm was the thing that decided how to place these different vertices and such. And I think it's done a fairly good job in this case. But I imagine that there is a more sophisticated way to place these things so that one can see the full extent of the nice geometry which is going on underneath this picture. For example, these blue edges here, these just represent multiplying by 2. So the blue edge pointing out of 1 points towards 2, the blue edge pointing out of 2 points towards 4, 4 to 8, 8 to 16, and so on and so forth. So all of these blue edges here just represent how these numbers can change when you multiply them by 2. And the red edges, they represent what happens when you multiply by 2 and add 1. And so you can see here again that we've got some kind of quite lovely lessons being taught to us just by looking at these very, very simple ideas. Let's look at the patterns of the numbers. So we've got a 1 in the middle, and then what's the next closest numbers? Well, then we've got 2 and 3. They're kind of on the next ring. You know, they're we can imagine sort of drawing a load of rings. So the first ring contains 1, the second ring contains the numbers which are the next closest, which will be 2 and 3. The next ring would contain the numbers which are the next closest, which would be 4, 5, 6 and 7. And the next ring would contain the numbers which are the next closest, which would be 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this is one of my absolute favourites, one of these examples. And so one of these functions here is 1 plus 3x. That would be the red one. So for example, the red arrow pointing out of 12 goes to 37, because 3 times 12 is 36, plus 1 is 37. And the blue edge represents 2x. So, 2 times 6 is 12, that's why the blue arrow pointing out of 6 points towards 12. Well, okay, so why do I like this? Well, I absolutely love it for 2 reasons. The first reason is because it's crazy. It's completely, the other examples we've just been looking at have been very regular, very kind of ordered, very easy to understand. Suddenly, we have this one, which is not very easy to understand. In fact, I'm going to try to make an argument that this is actually an immensely complex structure and probably the kind of thing that the human mind will never fully comprehend. So that's one thing I really like about it. It's like, boom, suddenly complexity has we've just collided with something very, very interesting and complicated. The second thing I really love about this is because it's related to a classic conjecture, which is one of the great unsolved problems in mathematics, something called the Collatz Conjecture. And I've tried to illustrate it here with this mathematical worksheet. So this is actually a really nice open problem. I think one of the wonderful things about mathematics in general is that there are actually lots and lots of really, really simple sounding problems which people have attacked for hundreds of years and not really been able to solve. And this is one of them. So the Collatz problem basically goes like this. You take any positive integer. If it's even, then you divide it by 2. And if it's odd, then you times it by 3 and add 1. Okay? So that's the operation that you do. And the Collatz conjecture says that if you take any even number and you keep doing, any positive integer, and you keep doing that type of operation again and again and again, you will eventually get to 1. So let's look at an example here. If we start with 6, well, 6 is even, so we divide it by 2. Then we get 3, this is odd. So according to our formula here, we should multiply it by 3 and add 1. We get to 10. 10 is even, so we divide it by 2, we get 5. And so on and so forth. You see, in this case, we eventually get to 1. And just incidentally, once we get to 1, we just sort of keep cycling. We go from 1, 4, 2, 1, 4, 2, 1, 4, 2, etc. So basically, the Collatz conjecture says that whatever number we start with, we always end up in this kind of cycle. It's fairly interesting. For example, if we start with 27 here, then it actually takes 111 operations to get back to 1. So this is one of the interesting things about the Collatz conjecture. Just by starting with a fairly small number, yes, it does end up going to 1 in this case, but the way it goes to 1 is kind of weird and not the kind of thing that we can easily understand, I think. Let's just plot this just for fun. Yeah, so you can see that the way this thing actually ends up making its way down to 1 is pretty strange. I mean, it goes all the way up to some very large numbers on its way back down to 1. Okay, so that's something about the Collatz conjecture. You might be wondering what on earth the Collatz conjecture actually has to do with this diagram here. Well, basically, what this is doing is actually sort of showing the Collatz conjecture in a sense, because our red arrows here, these are exactly representing these 3x plus 1 operations that we're supposed to do whenever we encounter a odd number. And the blue arrows here represent timesing by 2. And so we can actually restate the Collatz conjecture in terms of this network. Basically, an equivalent way to say it would be that if we start at any node, then we should follow the following recipe. If there is a blue edge pointing into our node, pointing into our number, then we should go backwards along that blue edge. That would correspond to dividing by 2. Whereas otherwise, we should take the red edge. Actually, this would be a better example. So, for example, here, we're at 6. There is a blue edge pointing into this, so we should go backwards along the blue edge. Then we get to 3. Now, there's no blue edge pointing into 3, because 3 is odd, obviously, so we should go outwards along a red edge. So basically, the Collatz conjecture can be phrased in terms of this network as follows. It says that if you start at any point, and then you always go backwards along a blue edge whenever there's a blue edge to go backwards along, or you always go forwards along a red edge otherwise, eventually you'll end up at node number 1. So basically we can couch the Collatz conjecture in terms of this network here. Now, there's just a small kind of extra thing I have to say, and that is that, of course, the complete network is not shown here. I'm only showing the numbers less than 128 here. So, for example, there should be a red edge pointing out of this node 108 here, but that would point to something bigger than 128, so it's not shown. But if we imagine the kind of infinite network, then that would be how the Collatz conjecture would be formulated in this case. Well, okay then, so we can couch the Collatz conjecture in terms of this network. Well, so what? It doesn't give us a way to prove it directly. In fact, I think from a kind of traditional mathematical viewpoint, one might say that, you know, this isn't really making any progress. But I think that it does give one a progress if one looks at things from a kind of higher level. Because let's face it, the Collatz conjecture is just one example of something that you can do with numbers which we don't understand very well. It's kind of more interesting, I think, to look at a more global picture. What other kinds of problems are similar? And why is the Collatz conjecture so complicated? Well, I think the second question is very interesting. Why is the Collatz conjecture so complicated? If we look at some of these earlier kinds of systems based on numbers, on these sort of 2 mappings, we see that they're very simple. And suddenly, when we get to this one here, involving 3x plus 1 and 2x, we find that the network's quite complicated. Okay, so a good question to ask then is, how complicated is this? Well, a nice way to get some insight is just to run the thing for longer. So here we're looking at all the numbers less than 128. Let's look at some more. This is all the numbers less than 600. And we still see that the network is pretty complicated, okay? In fact, down here, I think, somewhere down here, yes, here we have all the numbers less than 5,000. I've done a nice 3D plot of this. So basically each of these nodes is an integer, and they're linked when they should be linked in the Collatz kind of network I've been talking about. And we can see that the structure being created is fairly complicated. And although our eyes could be missing some kind of similarities, I kind of doubt it. I kind of think this is one of those places where Mother Nature's somehow managing to string out some serious complexity using some simple processes. So that's one application of our exploration. We can we can discourage people from trying to prove the Collatz conjecture. No, I'm only joking. I think that the Collatz conjecture will probably end up getting proved pretty soon, knowing how much ingenuity people tend to have. But what is interesting is that we can just look at the whole space of systems like this. Okay, so here we have 1 plus 3x and 2x, but we can have other things. So let's look at some other kinds of networks that get generated. Here's another one. And here we have 1 plus 4x and 2x. And we can see here that we're getting sort of tree-like structures being generated. I think the reason that we're getting trees here is because we're always getting one odd number and one even number being created, sort of like before. And we can get other funny things like this. So here we have sort of some funny structure on the left, and also there's kind of a long tail being created on the right. We'll see these kind of phenomena happen in many different types of networks. One of the interesting things about these number theory based networks is that they don't really grow in a sense. In a sense, they're just there. They're kind of if you're a Platonist, they're kind of already floating around in the space of different patterns of numbers. But we certainly see a lot of other things like this happen when we start to look at networks that grow. We often see that we'll end up with some kind of complicated ball thing that will end up growing out some kind of long shoot. And so here's another network. In this case, the red arrows are representing the operation 2 plus 2x, and the blue arrows representing multiplication by 2. And here we're seeing some sort of flower shape here. And one can see that some of these structures are kind of artistically interesting. I think if one made this picture for, for a lot more numbers, maybe with like 1,000 numbers, one could probably replace these with cylinders. Perhaps one could make some kind of nice necklace or pendant out of it. So it's interesting to think about these things from lots of different angles. What kinds of spaces have been created? What kinds of objects have been created? What kinds of lessons can we learn? There's many different angles to view these systems. And so here's another system. This looks pretty similar to the Collatz type system that I was talking about before, but it's actually a bit different. So if you remember before, we had 1 plus 3x and 2x. Here we've got 2 plus 3x and 2x, and again we're seeing a kind of complex looking network, but it looks very different, and it has different kinds of shape to it. And so basically we can see that Collatz example was not just it wasn't just a fluke. There's actually lots and lots of simple systems like that you can get just by looking at the interaction between two different mappings, two different functions, and they can make some very, very interesting shapes. And here we have another one. This is 3 plus 3x and 2x. And so once again we have more complexity being generated. So basically, even looking at these really, really, really simple systems just based on numbers alone, we can already start to find some very, very kind of interesting patterns. So I think when everyone's seen a lot of systems like this out there, it's fairly natural to ask, what kinds of other systems are there to find? And so basically there's just so many different kinds of systems based on numbers and networks that one can study. So for example, here we just have two mappings. If we simply have three different mappings, we get a multitude of new different kinds of networks, and I've had a little bit of exploration of those kind of systems, and perhaps I shall post a video later about what those kind of things look like. Certainly there are a lot more other kinds of behaviour that can be seen and so forth. Another thing that I've been looking at are systems based on complex numbers. Now, as I said before, I don't want this course to be very high level. I don't really want to talk about any concepts which, let's say, I don't want to rely on any concepts which are beyond the education level of a 16-year-old, because I just want to make this course accessible. But basically, complex numbers are generalizations of ordinary numbers. It's really quite a simple idea. You just include this extra idea of this extra thing called I, and I is the square root of -1, and you basically allow I into your set of numbers, so you have a bigger set of numbers to play with, and we call those complex numbers. But anyway, essentially we can do the same thing with complex numbers as we did before. We can just get a load of complex numbers, and we can define a couple of functions that represent different kinds of edges, and we can use those to generate different sorts of networks. So for example, here all our nodes, these are all the nodes with real or imaginary arguments with absolute value less than or equal to 10. And if we look, we find this node 10 plus 6i. Where is it now? Somewhere. There it is. So this is one of our nodes in our network. And these are our different functions. So if we apply this function here, this makes one kind of edge. Let's say this makes the blue edges, and this makes the red edges. So if we apply this kind of function to 10 plus 6i, blah blah blah, then we get -7 plus 9i, which is there. Okay, so basically this is just exactly the same idea as before. We define a couple of mappings, and we use these to make these two different kinds of edges which can come out of our different numbers. And why are we doing this on complex numbers? Basically just to make some nice shapes, to make some interesting networks. So here we see this shape here kind of looks like an ice cream cone, or maybe it'd be a nice way to sort of wrap up some roses or something, or maybe you could use it to make a horn or something like that. So basically this is a source of geometry. Of course we're relying on Mathematica's ability to do graph embedding to make stuff like this, but with complex numbers we don't actually have to. Complex numbers are naturally defined as having coordinates. Anyway, I'm trying to stop myself talking about complex numbers because I want to increase the audience of this lecture. So here are some other networks we can make, basically by doing these multi-way systems based on complex numbers. And you can see that there's a great variety of different shapes that we can make. And Really, it's just a matter of using your imagination and trying to think about what kinds of objects and what kinds of applications we can have for these different things. I mean, maybe you can see that we could slice this thing in half and make some kind of vase or table or chair, or I don't know. There's got to be so many interesting objects and pieces of art that we can make with these different patterns. But it just seems like such a interesting and difficult process to actually match the structures that we're getting created with actual applications. This one looks a lot like a tree, I suppose.
And so here's a 3D print of that spiral network that I made before. So you can see that the one in the middle here, and then if you remember, it's like adding ones as you go around the outside, and then it's like multiplying by 2 to travel outwards along the spokes. So, you know, one can make lots of fancy little coins and pendants and all different kinds of shapes just from these nice little things that come from geometry. Okay, and so I've also attempted to 3D print a version of that kind of flower holder thing, which came from the Multiwave system involving the imaginary numbers. My skills with 3D printing are growing, but they're growing slowly, and so you can see that there's some definite issues with this particular 3D network. However, certainly I could send it off to Shapeways or whatever to get it perfected. The point I'm trying to make here is that one can make a fairly large number of pretty interesting and original objects just by taking some of these things that you find, well, loads of mathematical systems, places like Multiwave Systems with numbers. You can find these very interesting shapes, and these days with Shapeways and so forth, it's a piece of cake really, just to convert the shape into an STL file, and you know, have it made out of metal or have it made out of plastic or whatever. If I would have made this larger and made it out of a more sturdy material, it would make a very nice vase or something like that to store flowers in.